Hey guys, so in this video I'm going to try and look at what I think are the trickiest level 2 organic reactions that you can come up against. The first situation I'm going to take a look at is the use of potassium hydroxide, which is aqueous, versus potassium hydroxide, which is in an alcoholic solvent like ethanol. And then the second situation I'm going to take a look at asymmetric addition and Markovnikov rule. So for the first section here, we're going to take a look, as I say, at potassium hydroxide, which is dissolved in water. Water is typically your solvent in most chemical reactions, versus potassium hydroxide, which is dissolved in an alcohol like ethanol. So typically, if you use potassium hydroxide, whether it's aqueous or alcoholic, you'll get a mixture of substitution and elimination going on. But if you use potassium hydroxide aqueous, you predominantly get a substitution reaction. Whereas if you use alcoholic potassium hydroxide, you get an elimination reaction. So that's the first big difference between those two reagents. So this little bit in the brackets here is very important to tell you what type of reaction you should be getting. So for NCEA level 2, if it's potassium hydroxide aqueous, it's a substitution reaction. And if it's potassium hydroxide alcoholic, it's an elimination. So if we take a look at a haloalkane here, so this is going to be 2-bromo butane we're doing. So 2-bromobutane, that means you have a 4-carbon chain. You guys need to make sure you practice your naming to be able to draw these molecules as fluidly as this. So 2-bromobutane is right there. And if we set up the same situation then on the other side, we'll take a look at what happens if you treat it with alcoholic potassium hydroxide. So another 2-bromobutane over here. And there's your bromine there as well. So if we treat this with potassium hydroxide aqueous, we get a substitution reaction. This is pretty straightforward to take a look at what the product's going to be. If I use green again for the skeleton of the molecule, so it's going to be CH3, CH2. Carbon is here. This is the central carbon. I like to refer to this as the central carbon, by the way. So the central carbon, which is where most of the action takes place. And in this case, you have a substitution. It's called nucleophilic substitution, where nucleophile is anything with a negative charge. So it either has a full negative charge, like a bromide ion, or it carries lone pairs of electrons, like on ammonia, for example. So in any case, there's a negative charge carried on it. So the nucleophile swap here is the OH group from the potassium hydroxide is swapped for the bromine, and therefore you get, as your product here, you get an alcohol, and this would be butan 2-ol, so you indicate the position of the OH group. But as well as that, so the bromine has come off, and then it will bond with the potassium ion there, so you'll also get KBr as well. So that's nucleophilic substitution if you're using potassium hydroxide aqueous. Now what happens if you had your 2-bromobutane and you didn't want it to form an alcohol? So you don't want it to form an alcohol. Well, the way you do that is you use your reagents, you use potassium hydroxide, which is dissolved already in an alcohol. And effectively, it's a bit like the Le Chatelier's principle. If the system already has plenty of alcohol, well, then it's going to form something else. And that's a basic enough explanation. You're not asked to explain this in your examinations, other than to say that by using potassium hydroxide alcoholic, it prevents this production of alcohol and encourages an elimination reaction instead. So that would be sufficient for an excellence. They're more interested in, can you predict the two possible products that will come off this elimination reaction, because you're going to have a major product and you're going to have a minor product. And this brings in a guy called Zaitzef, the two Russian chemists that you need to be aware of when you're dealing with your organic chemistry. And Zaitzef's rule is as follows. So I'll write it up here. The carbon more likely to lose the hydrogen is the one with the fewer hydrogen. Sometimes your books like to refer to as the poor get poorer. So the hydrogen poor carbon will get poorer. Now we're not talking about the central carbon, that we can't touch that. and the bromine is going to be eliminated from there. So we're looking at either carbon either side of that central one. And in this case, the most poor carbon is that one. So the minor product is going to be CH3CH. One of the hydrogens has been removed, so the double bond is established here. The bromine is gone as well from that, so this is removed, and one of the hydrogens are removed, and then you get CH3 on the end. In green there, just to show you, we will have HBr as well as a small byproduct. So in an elimination reaction, you always get a double bond being formed, and you also get a small byproduct. And that's the major product. What I've just drawn there. So that's the major. The minor is going to be the opposite situation, and this would be a much lower percentage of the product. But this is where the actual carbon with the more hydrogens is going to have its one eliminated. So the double bond would be formed on this end. Your hydrogen is still there, your bromine is gone, and you'd have CH2 here and CH3. And plus your minor product of HBr again. So your major product here would be bute-2-ene. So you formed an alkene, bute-2-ene and hydrogen bromide right there. And in this case, it would be bute-1-ene and hydrogen bromide. So that's Zaitzef's rule. So Zaitzef's rule again, when you're dealing with elimination on a haloalkane, for example, or this can also be with an alcohol going to an alkene, you look at the central carbon, which is this one right here, which has the functional group attached to it, and then you look at each carbon either side of it and decide which one has the least number of hydrogens, and that is the one that you eliminate most from, which gives you the major product, and then the other carbon is eliminated from in minor circumstances, and you get a double bond formed and a little byproduct as well. So that's how you go from an alcohol or a haloalkane to an alkene. But the key point we're trying to make here is that just from that change from aqueous potassium hydroxide to alcoholic potassium hydroxide, we are now encouraging the formation of an alkene rather than an alcohol from before. Okay, so for the second half of this video, I'm going to take a look at asymmetric addition on an alkene. Normal addition on an alkene, which is not asymmetric, involves molecules like hydrogen, which both atoms are the same, therefore it's symmetrical. Another example could be molecular chlorine or bromine, in which case both atoms add on across the double bond, and there's no distinguishment between which one of the carbons involved in double bond gains those extra elements. But when you're dealing with asymmetric addition, so this is the addition of a molecule which is asymmetric. So if you look at water, water actually breaks up into H plus ions and OH minus ions, so that's an asymmetric split of the molecule. HBr is another example. It will split up into H plus and Br minus ions. So these are two examples of asymmetric addition. And sometimes when you have asymmetric addition, or usually if they're assessing you on asymmetric addition in your level 2 chemistry, it's going to be to check if you understand Markovnikov's rule. And Markovnikov's rule is that the carbon involved in the double bond, so there's always two of them, there's two carbons to look at. The one which is most likely to gain the extra H plus is the one with the most hydrogens already. In other words, the rich get richer. So if we look at the addition of water, first of all, onto prop-1-ene, the carbon with the most hydrogens is this one. So therefore, your major product is going to involve that carbon gaining an extra hydrogen. So we'll just put it on here at the end. So we'll call that the extra hydrogen. That's coming from here. And the double bond is now broken, and you have a situation where the OH group is then going to be added on here. So with addition reactions in alkenes, all of the reagent is added on to the alkene. So there you can see your hydrogen was added to the carbon which had the most hydrogens in the first place, and therefore the OH group goes in the other one. This would be your major product, and there's no small byproduct because all of the reagent was added on to the main molecule. And this one would be, this is an alcohol, so it's propan-2-ol. The minor product then is going to be the opposite situation, so it's going to be where the OH group is here, and then your two hydrogens are right here, and then the extra hydrogen was added on at this position instead. That would be your minor product, and that would be propan 1-ol. That would be your minor product. So that's an example of asymmetric addition and considering Markovnikov's rule. Another example you could have, as I say, would be the asymmetric addition of HBr, hydrogen bromide, onto propanene. Again, the products are going to be based on the carbon which has the most hydrogens as the major one. So if we start off with this one again, the hydrogen in this case is coming from here, so we put that one right there. The double bond is broken every time with an addition reaction on an alkene, and the bromine is going to have to go here, and then your methyl group at the end there. So this major product, the major product for this addition reaction would be known as 2-bromopropane. And then your minor product would be the opposite scenario again. So the bromine is added here this time. The double bond is broken, and the extra hydrogen is added on there on that carbon. And then you get the CH3 at the end, and that would be 1-bromopropane. So that's a little review of Markovnikov's rule for asymmetric addition on alkenes. And in my mind, they're the trickiest, some of the trickier ones that you could be assessed on in your level 2 organic chemistry. So make sure you practice lots of Markovnikov and Zaitzef elimination addition reactions.